We have built the Laplace toolkits: definition, shifting rules, inverse Laplace, poles, zeros, and endpoint checks. Now we connect that toolkit back to real circuits. The goal is simple. Take each time domain element and replace it with an algebraic model in the S domain. Resistors will look almost unchanged. Inductors and capacitors will carry memory, so their initial current or initial voltage becomes a source term. Once we can do this, the next lesson can write node and mesh equations directly in S. The dividing line is energy storage. A resistor does not store energy as a state, so it has no initial condition term. An inductor stores magnetic energy, and the state variable is its current, IL of 0 minus. A capacitor stores electric energy, and the state variable is its voltage, Vc of 0 minus. The 0 minus notation matters. It is the value just before switching. The S-domain model must remember this stored energy, otherwise the transient part of the answer disappears. Start with the resistor, because it is the clean reference case. In the time domain, VR of t equals R times IR of t. The Laplace transform is direct. VR of S equals R times IR of S. No derivative appears, so no initial condition appears. In the S-domain circuit, the resistor is still just R. This is why resistive parts of the network become ordinary algebra, while storage elements bring the extra memory terms. For an inductor, use the passive sign convention. Current enters the positive voltage terminal. The time domain law is VL equals L dIL over dt. The Laplace derivative rule gives VL of S equals L times SIL of S minus IL of 0 minus. So VL of S equals SLIL of S minus LIL of 0 minus. Read this as an impedance SL plus a series source term caused by the initial current. The inductor is not only an impedance, it also remembers its current before switching. For a capacitor, the stored variable is voltage. With passive sign convention, IC equals C dVc over dt. Taking the Laplace transform gives IC of S equals C times SVC of S minus VC of 0 minus. If we solve this for voltage, Vc of S equals IC of S over SC plus Vc of 0 minus over S. So the impedance is 1 over SC, and the initial voltage appears as a series voltage source. The capacitor remembers voltage exactly the way the inductor remembers current. Put the three models side by side. The resistor is R. The inductor is SL with an initial current source term Li0 minus. The capacitor is 1 over SC with an initial voltage source term V0 minus over S. The signs are not arbitrary. They come from the derivative rule and the chosen reference directions. If a branch current or voltage reference is reversed, the algebra changes sign with it. The safe method is always to write the element law first, then transform it. Now a tiny example. A capacitor starts with voltage V0 and then discharges through a resistor R. The current through the capacitor plus the resistor current must sum to 0, so C dV over dt plus V over R equals 0. Taking Laplace gives C times S V of S minus V0 plus V of S over R equals 0. Collect V of S and we get V of S equals V0 over S plus 1 over RC. In time domain, this is V0 e to the minus t over RC. The pole is at minus 1 over RC. There are 4 common traps. First, use 0 minus, not 0 plus, for the stored initial value before the switching event. Second, do not invent an initial source for a resistor. Third, do not memorize the source polarity blindly. Derive the sign from the reference directions. Fourth, do not drop the initial term just because there is no external input. A natural response is driven exactly by stored energy. Summary. A resistor stays R in the S domain. An inductor becomes SL and remembers its initial current. A capacitor becomes 1 over SC and remembers its initial voltage. These source terms are the bridge between physical stored energy and algebraic circuit equations. Next, we will use these models to write node and mesh equations directly in the S domain, then solve the transient response as algebra.